Welcome back to the afternoon session. Now we're going to have Antonio Pedro Ramos, who's going to talk about Fourier optimization and pair correlation problems in number theory.
Okay, thank you, Tainara, for the introduction. Also, thank you to the organizers, Mateus, Felipe, and Manuel, for organizing this nice conference and giving me the opportunity to speak here. So today I'm going to talk about how to obtain certain bounds related to number theory using the pair correlation of sequences in number theory using the framework of Fourier optimization. Whoops. And so the beginning of the story, as is usual in anything in analytic number theory, is the Riemann zeta function. And so I'm going to review some classical facts about why we care about this function. And so the zeta function is a function that depends on a complex parameter S. Initially, it's defined by this, for S with a real part strictly greater than 1 to make sure that this definition, the series definition, makes sense. So this not only converges absolutely for these values of S, it converges uniformly in compact subsets of this plane. So this is an analytic function. And also, as observed by Euler, this is intimately connected to primes because of the Euler product for factorization. So something that every mathematician knows is the fundamental theorem of arithmetic. Every positive integer can be uniquely factored as a product of prime powers. So in an analytic way to say this is that this series, this infinite series, factors into this product over primes of the geometric series in 1 over p to the s. And as long as these two things converge, this identity should hold, and this is equivalent to the fundamental theorem of arithmetic. So because this middle term is the geometric series, you have this very nice compact way of stating the same thing. This, for both these definitions, for both these representations, the convergence is in this half plane. But there's a standard way to extend this function to C, to a meromorphic function with a single pole at S equals 1. And one way to see how this is connected to primes, basically a very easy observation, is to use the fact that it has a pole to show that there are infinitely many primes. So if the modulus of this function blows up as you approach 1, and you can look at the Euler product factorization here, and you see each of the factors here is an analytic function. So if we had finitely many primes, this thing would obviously converge to some value, some finite value. Now, one property that emerges from this analytic continuation is that the zeta function has a symmetry about the line real part of S equals 1/2. And so you can relate the values of zeta of S to zeta of S of 1 minus S, admitting some sort of coefficient here that also depends on S. So we have these known guys, some exponential term here, a sine, and a gamma function. And just from this equation here, the functional equation, you can see that zeta has to have some zeros. So sine of pi of S over 2 has zeros at the even integers. Some of these zeros will have to cancel out with the poles of the gamma function. But the gamma function is also analytic in a half plane. So zeta has to have zeros at the negative even integers. And these are what we call the trivial zeros of the zeta function, because we know exactly where they are and we know exactly how they contribute to the story. And another consequence of the functional equation and also the Euler product representation is that the zeta function cannot have other zeros outside of the strip here between 0, real part of S 0, and 1. And so just a picture to illustrate what I've been saying. You have the trivial zeros at the negative even integers. You have the critical strip. It's bounded here by real part of S equals to 0, real part of S equals to 1. And in the middle here, you have the critical line. And so there's this famous, the conjecture by Riemann hypothesis, where all the other zeros of the Riemann zeta function would have to be aligned along the middle of the strip. And in fact, there have to be a lot of zeros in this strip. So one thing that you can do is apply the argument principle. You can draw a large box. You can draw a large box around the strip. So a box containing 0 to 1 and going up to a height t. And you do this contour integration, and you get that you can approximate the number of zeros in this box, the zeros of zeta. And this has to be asymptotically equal to t over 2 pi times log t. One illustration of the principle that zeros of the Riemann zeta function tell us information about arithmetic is that the fact that zeta does not vanish on the boundaries on the boundary of the strip, that is when the real part of S equals to 0 or 1, this is a fundamental step in the proof of the prime number theorem, which basically tells us how we count primes up to a certain number, positive value x. So if you're counting, you have a positive value x, the number of primes up to that point is asymptotically equivalent to x over log x. And this is the prime number theorem. So one of the greatest advancements in the theory of the Riemann zeta function was due to Montgomery, who realized that, okay, so after Riemann, people saw that many consequences to arithmetic were due to the fact, would follow from the fact that the zeros of zeta are aligned along a single line. This is a fact about the horizontal distribution of the zeros. But Montgomery asked, so what if we know something about how they are distributed along this line, how they are distributed vertically? Can we get even finer information about primes? And this is the philosophy that guided him to study pair correlation of zeros. So imagine a typical zero of the Riemann zeta function under the Riemann hypothesis. So it's basically the real coordinate is 1/2 plus I gamma, gamma being the interesting part here, the ordinate. And he conjectured a fact about the distribution of the pairs of zeros. So if you count the number of pairs that are within some normalized distance, 2 pi beta over log t, beta is a parameter, positive value, and you normalize over the number of zeros, you should get asymptotically as you look at larger and larger heights. This should be given by this integral from 0 to beta of this function here, this density 1 minus sinc squared. And so proving a fact like this would, for example, have consequences, better bounds on large gaps between primes, better estimates on the error term of the prime number theorem, and things like that. And would it also have consequences for analytic facts about the zeta function itself, which are of interest, like, for example, saying that whether the zeros of the Riemann zeta function are simple or not. So to study the differences of these ordinates, gamma minus gamma prime, Montgomery introduced this function, which is a kind of a Fourier transform. So it's a function depending on a parameter alpha, which is a real number, and a parameter t, which is positive number. It's going to be a height. And you're going to do this exponential sum over all pairs of zeros up to a certain height in the critical strip of this oscillatory factor here, t to the I alpha gamma minus gamma prime, times a weight here that just allows us everything to converge properly and introduces a nice decay. So the conjecture that I said of Montgomery can be equivalently stated as this statement about averages of this f function. So averages in these intervals outside from b to b plus l of the f function should be asymptotically equivalent to 1, as you go to larger and larger heights, and there's a formulation due to Goldstone. And of course, this is a very hard problem, but one way to achieve some kind of partial progress towards this conjecture is to provide good upper and lower bounds for averages of this function. And some work has been done on this, first by Goldstone himself. So he found this lower bound of 1/3 and upper bound of 8/3. This upper bound of 2 is due to Goldstone and Gonek. And then the previous best bounds were due to Carneiro, Chandi, Chire, and Milinovic, which gave lower bound as 0.9278, upper bound as 1.3302. And together with Emanuel and Micah Milinovic, we managed to improve the upper and lower bounds to 0.9303 and upper bound to 1.3208. And though this may seem like a modest improvement in the constants, it's still interesting because it has the advantage of considerably streamlining the previous result of Carneiro, Chandi, Chire, and Milinovic, and it establishes a relation of these bounds with a nice Fourier optimization problem using a new averaging mechanism. And so just a little bit about the proof of this fact. We do a convenient approximation of the characteristic function of an interval. We pick a test function g, which will satisfy some nice properties. I'm going to talk about them a little later. And we do some convolution with it to construct this approximation phi of L. And so you will replace here the characteristic function of the interval b to b plus L by this shifted version of our function phi. And we apply Fourier inversion on this last integral, and you get this large expression. But it looks scarier than it is because essentially here you have a unimodular factor, again bound above by 1. Here you have Fourier transform of a characteristic function of an interval, which we know is a sinc function. And here you have our test function g. And so you can upper bound this by just the following simpler expression, which is just L times the sum here of g evaluated at these differences, gamma minus gamma prime, appropriately normalized. And so you do Fourier inversion again, and you get that this is exactly the integral. This sum here is exactly the integral of g hat against Montgomery's function f alpha. And using the asymptotics of this function, following the work of Goldstone and Montgomery, we get that this integral here in the limit is g hat of 0 plus this integral of g hat, this weighted integral. And now we have this nice bound here, because on one side you have the integral of the f function over an interval, which is what we want to evaluate. And on the right-hand side, here below, we have something that depends on a test function. And we can get the best bound possible by optimizing over the choice of the test function g. And we essentially run into this Fourier optimization problem, which is you want to minimize exactly this quantity. This is g hat of 0 over g of 0 plus this 1 over g of 0 times this integral depending on g hat over the class of functions, integrable functions, such that the Fourier transform is also integrable. Fourier transform is non-positive outside of the interval minus 1 to 1. And the function itself is positive for all alpha. And so this is a kind of prototypical Fourier optimization problem, because essentially we're trying to optimize something that depends on both g and g hat, and you're also placing these restrictions on both the Fourier side and the physical side. And now these are usually very delicate problems, and so it's difficult to solve them exactly. And so we have two approaches that we use to tackle these problems. One is to draw on some numerical work done before by Chira, Gonçalves, and Delat, which worked over this class of functions to try to estimate this minimum, and so working over the full class. And the second approach is to use reproducing Hilbert kernel Hilbert spaces to try to estimate these values. And just one word about this second method is that essentially if you tighten the middle condition, and so if you force here g hat to be exactly 0 outside of the interval minus 1 to 1, essentially you have a function that's band limited. So as we know by the Paley-Wiener theorem, a function g is going to have to be entire and has to have exponential type, and you end up in the context of Paley-Wiener spaces. And so you can use this theory. And of course, if you tighten a condition here, you in principle, you get worse bounds. But this has the advantage that somehow you can get a more structured answer. So if you vary a bit parameters in this functional, it's more or less easier to get some kind of answer. And so why do I say this? Why do I care about changing the parameters? Is that essentially we want to generalize this approach to other sequences of zeros of L functions coming from number theory. So for example, for those of you who know some analytic number theory, other Dedekind zeta functions or primitive elements of the Selberg class, or in general Dirichlet series and similar objects, because essentially to use our method, we are using very weak conditions on these sequences of zeros, which are all shared about among all these objects. And so we can bound the averages of analogs of the f function for all these objects, essentially by looking at this class of Fourier optimization problems, which is you're trying to minimize the integral of g hat with respect to a certain measure, a measure nu that in the examples we're interested in usually has this form. So it's basically a Dirac delta times a parameter times an absolutely continuous part that has these two parameters here. And now, just as one application of this is that you can do the same sort of game for, say, the real and imaginary parts of zeta, which the zeros of the real part of zeta is a considerably different object than the zeros of zeta itself. And so in principle, you can't say just from one side, you can't draw implications to the other. And so you have this kind of bounds for the form factor, the analog of Montgomery's function. And one corollary of our bounds is that we managed to disprove a conjecture of Gonick and Key about the zeros, the pair correlation of zeros, the real part of zeta, along lines to the left of the critical line. So if you think about that picture, you have the middle of the strip, and you're looking at lines that are exactly to the left of that critical line. And this is all I have for today. Thank you.